I'm in the science research. And so we deal with mostly, after everyone has done with the processing of the data, we take the data and try to process the data to do some science with it. And I think Contra has already spoken about a nice image there. One thing to mention with that image, because of the high resolution and sensitivity as well, we're able to pick up those tiny filaments. We believe those are magnetic fields, but what kind of mechanism generates that, we don't know yet. But the stuff in our Milky Way galaxy that we still don't understand, and MeerKAT has been great at that as well. Another one is here, studying gravitational waves. So black holes, when they do their stuff, they spin, they dissipate gravitational waves. We already have a gravitational wave detection observatory, LIGO, but it's kind of on Earth and it's limited, okay? But timing out pulses, you can then try to figure out gravitational waves generated by small black holes, okay? LIGO is great at when two black holes, big black holes, are merging together, and you can trace out, learn the mechanism of those. So MeerKAT does this with pulsars, okay? And I'm not gonna explain the pulsars. Enough. Let's leave it there for now, okay? All right. But one aspect is gravitational waves, okay? Another aspect here, you can see this is a galaxy, okay? And this is the optical as a background with an optical image, okay? But if you want to learn more about the mechanisms driving how galaxies form and all that kind of stuff, we make radio images as well. It turns out the gas surrounding this galaxy emits a certain kind of signal that can trace. So what you're seeing over here is the neutral hydrogen around there. And you can see the galaxy is still pulling, so there's still a lot happening. Something that you won't be able to see if you only had the optical image. So there's a lot of dynamics that MeerKAT is actually informing the science. And then also over here, we have star formation rates, which we try to share about basically MeerKAT as well. So it's kind of a confirmation here. We already know how star formation rate occurs in the optical region, but now with MeerKAT, this is fantastic. The last one, before I start confusing you, that one. So galaxies also do interesting kind of stuff. They can collide together, right? And they leave these kind of shock waves. Okay, when they collide together, they leave these shock waves. And MeerKAT is excellent at detailing this neutral hydrogen that's on the edge, is detailing that shock wave. I mean, people who study these things will tell you all about how that influenced the dynamics of the mergers between black holes. People like you, people like me. And then the best one of all of them is this collaboration with MeerKAT with the other telescopes. So if you've seen the nice black hole image that was made using several antennas laid around, you need a high resolution, so you combine all of those antennas. But now MeerKAT is going to be part of that network of antennas. So over here is what you would see without MeerKAT. But the moment you include MeerKAT, the image improves a lot brighter. Maybe you may not see it. Yeah. And that's where we're going. Right. And this will give us more detailed images of black holes, because now MeerKATs can be incorporated into the BBR.
What's the difference, actually? Sorry? Once it is, what's the difference in what you can see without MeerKAT in what you can see?
So if you incorporate MeerKAT, you can see a lot of details. Okay? So the BBR network already have the largest baseline, but you want to improve what we call the point spread function. Okay, that how the telescope responds to it. Without MeerKAT, it's built all over the place, but the moment you do MeerKAT, it's just slightly better. Okay. All right. Thank you guys for listening to me.
So, Omar will. So because we can't always bring people out here, we thought we should do a demonstration of what we do. So Omar's team edit people also.
Today we have MeerKAT. This is a smaller version. We call it MeerKitten. And we use it as an educational and outreach tool. So this was all designed at our lab in Cape Town. This is 3D printed. We have basically the USB type connectors, so they're connected to each other, and you can expand the array as large as you'd like to. And we use this to demonstrate to people the concepts of radio interferometry. So it's controllable using especially for kids, this is very useful because it's something that they can all relate to. And it has different modes that we use. So for example, you can control all the antennas at one time, or you can select certain arrays or sub-arrays that you can control. So yeah, we would normally, for example, have an image that we would display and would show them, using one telescope, this is the image. And as we bring up more telescopes, we'll show them maybe, the image improves, this will be effect of resolution and so on.
Yeah. Especially also showing the IGBN array. So what if will you?
And what's also good about it, what we'd like to do eventually is have kits for kids to build, because designing this, mechanical engineering to get the model, the circuitry, a lot of electrical engineering, programming it is, software, computer engineering. So it brings together all the different aspects of engineering to build this. Thank you so much. Thank you. Welcome.
So just behind there is some of the people over time that have been part of our HCD program. I was actually with Precious last week at UKZN. She's lecturer. She started her junior degree on our HCD program. She's lectured it is. And then I think this was from our last Coastline conference. So every year we had this conference where we divide all our postgrad students, and then they come present their papers, they get to network, and we really actually hope and be no, guys. An astronomer is not a white-haired lady.